Hi, boys and girls. In this section we are going to recap the topic of gravitation, which is one of the new topics in KSSM syllabus. So in this video we are going to recap on what we learned and how to solve the questions involving the gravitational formula and laws. We hope that this video will help give your revision a boost. So, let's start our journey. Why would you land on the ground instead of floating off into space? Why did the apple fall down to the ground, and not up, or sideways? Yes, the answer is gravity. As we know that, gravity pulls things to the center of the Earth. Gravity pulls on things on Earth, but not in space because astronauts floats. It also pulls things and makes them fall down. So, what if there is no gravity? You are right. Humans and other objects will become weightless without gravity. If we have no gravity force, the atmosphere would disappear into space, the moon would collide with the Earth would stop rotating, we would all feel weightless, the Earth would collide with the Sun, and as a consequence. Do you know that? Every object in the universe, whether small or large, exerts a force on every other object. This force is known as gravitational force. Now, let's recap what we've learned in subtopic 3.1. Newton's universal law of gravitation. Two objects in universal were put on force between each other, known as the gravitational force or universal force. Gravitational forces exists in pair with same magnitude. It can be explained with Newton's universal law of gravitation. If you look at the diagram below, the attractive force between any two objects with non-zero mass separated by a distance. Now look at this picture. Do Earth and Moon experience the same gravitational pull? The answer is yes. Gravitational pull is a force. The two bodies each experience a gravitational force of the same magnitude. And the gravitational forces always exist in pairs. So, both pull towards each other with same force. We said that force exerted by Earth on Moon equals force exerted by Moon on Earth. Now let's look at the second picture. From the previous question, now we know that Earth exerts force on apple, and the apple also exerts force on Earth. But, why does an apple fall toward Earth instead of Earth moving toward the apple? This is because both the apple and the Earth experience the same gravitational force. This causes the apple and the Earth to move towards one another. As the mass of the Earth is very much larger than the mass of the apple, gravitational force does not have an apparent effect on the Earth's movement. As such, we only observe the apple falling to the ground. In 1687, Isaac Newton proposed two relations involving the force of gravity between two bodies. He realized that the motion of a falling apple and motion of moon were both actually the same motion, caused by the same force, which is the gravitational force. The force of gravity is directly proportional to the product of the masses of two bodies. The force of gravity is inversely proportional to the square of the distance between the centers of the two bodies. Since the gravitational force, F is directly proportional to the product of mass of objects and inversely proportional to the square of the distance between them. So, we have the gravitational force formula. F equal to capital G product with m1 and m2 over square of r. Where F is gravitational force between two objects. G is the universal gravitational constant. m1 is mass of first object. m2 mass of second object. R is distance between the center of two objects. Actually, form the formula of gravitational force, we can easily to find out the relationship between the mass of the object and their distance. As we know that F is directly proportional to the mass of objects and inversely proportional to the distance between the objects. From the table below, we find that the longer the mass of the body, the larger the gravitational force. When the mass of the body decreases, the force also decreases. On the other hand, if the distance between the bodies increases, the magnitude of the gravitational force will be decreased. The further the distance between the bodies, the smaller the gravitational force. So, we can conclude that the gravitational force is directly proportional to mass of the objects, and inversely proportional to the distance between them. So now, can you tell me what are the factors that affect the gravitational force? Yes. The answer is mass and distance. As the mass increases, the gravitational force increase. However, as the distance increase, the gravitational will be decrease. Okay, now let's us look at the effect of mass on gravitational force and the effect of distance on gravitational force. When the mass both object is m, then the gravitational force is F. If one of the objects now become 2m, then the gravitational force will be 2F. For the case number 3, if both of the objects is 2m, then the gravitational force will be 4F. So, if one of the objects is m, and the other one is 3m, then the gravitational force would be 3F. Now, let's us look at the effect of distance on gravitational force. If the distance between the two object m is d, and the gravitational force is F. What will happen to the force if we increase and decrease the distance between the objects? For case 2, if the distance between two objects m become 2d, so the gravitational force will be 1/4 times F. If the distance between two objects m become 1/2d, then the gravitational force will be 4F. If the distance between two objects of 2m is 2d, then the gravitational force will be F. From here, we can see that, as the mass increases, the gravitational force increase. However, as the distance increase, the gravitational force will be decrease. Even though gravity is a universal force, however, two people on the surface of the Earth will not feel the effects of gravity on each other. This is because the gravitational force between bodies of small mass has a very small magnitude. It can be negligible if we compare to the gravitational force of Earth. For example, two people, who weigh 50 kilograms and 70 kilograms respectively, only experience 2.3 by 10 to the power of -7 Newton, if they stand 1 meter away from each other. Now let's move on with some questions on gravitational force. In order to get the correct answer, there are several steps you need to follow. 1. List the given information in symbols. 2. Identify and write down the formula used. 3. Substitute numerical values into formula and perform the calculation. Example 1. Calculate the gravitational force between the durian and the Earth. Is given that the mass of the durian is 2 kilograms and the mass of the Earth is 5.97 times 10 to the power of 24 kg. Distance between the center of the durian and the center of the Earth is 6.37 times 10 to the power of 6 meter. So first, list the given information in symbol. Let the m1 equal to the mass of durian, m2 is the mass of the Earth. R is the distance between the durian and Earth from the center. And capital G is the universal gravitational constant. Then, we identify and write down the formula used. We are going to use the formula of gravitational force. Lastly, we substitute all the numerical values carefully into the formula, then we use the calculator to get the final answer. So, the final answer for this question is 19.63 Newton. Example 2. A rocket is at the spaceport, experiencing a gravitational force 4.98 times 10 to the power of 5 Newton. What is the mass of the rocket? is given. Mass of Earth equals 5.97 times 10 to the power of 24 kg. Distance between the center of the Earth and the rocket equals 6.37 times 10 to the power of 6 m. So, we list out all the given information in symbols, F, M1, M2, R and G, we write down the gravitational formula, F equals gxm1 xm2 divided by square of R. Then substitute numerical values into formula and perform the calculation. By using the formula F equals mg, and the gravitational force that pulls objects toward the center of the Earth, F equals product of with the masses of two bodies over the R square. Let equation 1 equals equation 2. Then, we can get the formula of G equals to big G times m over square of R, where the G is the universal gravitational constant. M is the mass of the Earth. R is the distance between the center of two objects. Form this equation. We know that G is the universal constant, let m is the mass of the object. If the mass of object m increase, what happened to the gravitational acceleration, g? Yes. The gravitational acceleration will. If the value of universal gravitational constant and mass of the Earth are constant, then, what are the factors affecting the gravitational acceleration? Yes, the answer is r, which is the distance between center of the Earth and the object, r only. As the distance increase, the gravitational acceleration, g, will decreases.
Let's derive formulas to calculate the gravitational at different distance relative to Earth's surface.
Now, let's study the diagram, and derive formulas to calculate the gravitational at different distance, relative to Earth's surface. For case number 1, if the object is below the surface of the Earth, the gravitational acceleration will be big G times mass of the Earth, m divided by square of r minus h, where the capital G is the universal gravitational constant. For case number 2, if the object is on the surface of the Earth, the gravitational acceleration will be big G times mass of the Earth, m divided by square of r. For case number 3, if the object is at a certain height from the surface of the Earth, the gravitational acceleration will be big G times mass of the Earth, m divided by square of r plus h. The diagram below shows the shape of graph of the variation of the value of the gravitation, g, with the distance, r, from the center of the Earth. From the graph, we find that when distance are less than capital R, the radius of the Earth, gravitational acceleration, g, the value g is directly proportional to the distance from the center of the Earth. It means that when r increase, the g will also increase. However, if the distance are greater than or equal to capital R, the radius of the Earth, gravitational acceleration, g is inversely proportional to the square of the distance from center of the Earth. It means that when the distance far away from the surface of the Earth, the gravitational acceleration, g, will be decrease. As conclusion, the gravitational acceleration is different based on the mass of the planet or moon, and the distance from its center of mass and its surface. For that reason, gravity has a lesser pull on bodies of smaller mass than the Earth. The following diagrams show the mass of the planet and their gravitational acceleration. Now, let us try to solve the questions involving the gravitational acceleration. Example 1. The diagram shows object A on the surface of the Earth and object B at height h from the Earth. Capital R is the radius of Earth, small r is the distance of the object from the center of the Earth, and m is the mass of the Earth. A. Based on the information above, derive the gravitational acceleration in terms of g, m, r and h for 1. Object A. 2. Object B. For question 1. As we know that, the object A distance from the center of the Earth is small r, and it is equal to the radius of the Earth, big R. Hence, the gravitational acceleration, g, is equal to capital G, universal gravitational constant, times m, the mass of the Earth divided by distance between center of the Earth and the object r, square. Question 2. As we know that, the object B distance from the center of the Earth is equals to r plus h. Hence, the gravitational acceleration, g, is equal to capital G, universal gravitational constant, times m, the mass of the Earth, divided by distance between center of the Earth and the object, r, plus, h, square. Question B. Given the mass of the Earth is 5.97 by 10 to the power of 24 kg, radius of Earth is 6.37 x 10 to the power of 6 meter, universal gravitational constant is 6.67 by 10 to the power of minus 11 n meter square per kilogram square. Calculate. 1. The value of gravitational acceleration of object A. In order to get the correct answer, first we give an information in symbols. Then, identify and write down the formula used. In this question, B1, we are going to use the formula G equals to big G times m divided by capital R square. Substitute numerical values into formula and perform the calculation. The final answer is 9.81 Newton per kilogram. Question 2. As we know that, the object B distance from the center of the Earth is equals to r plus h. Hence, the gravitational acceleration, g, is equal to capital G, universal gravitational constant, times m, the mass of the Earth divided by distance between center of the Earth and the object square of, r plus h. Let's try this. Good job. What is your answer? Were you able to get the correct answers? If an object moves in a circle, there is some net force acting on it, causing it to deviate from its straight line path. For examples, as a car makes a turn, the force of friction acting upon the turned wheels of the car provides centripetal force required for the circular motion. As a bucket of water is tied to a string and spun in a circle, the tension force acting upon the bucket provides the centripetal force required for circular motion. As the moon orbits the Earth, the force of gravity acting upon the moon provides the centripetal force required for circular motion. There are three types of the centripetal force, which is friction, tension, and gravity. So in these sections we're going to recall the centripetal force of the gravity that you have learned. With centripetal force, the object moves in a circular path with speed. When the centripetal force is removed, the object moves along the tangent to the circle path with a speed. So, what is centripetal force? It is a force that makes object to follow a circular path, with direction always, towards the center of curvature. The formula of the centripetal force, Fc acting on the object, is equal to m times v squared over r. Where the m is the mass of an object, v is the velocity of the object, and r is the radius of the circular path. As we know that, if an object experiences no net force, its velocity will remain constant. The object is either at rest and the velocity is zero, or it moves in a straight line with a constant speed. However, in an orbit, object is always changed its direction. There is a force acting on the object in the directions towards the center of the circle or orbit, which we called its centripetal force. The combination of uniform velocity and the centripetal force acting on the satellite will cause the satellite to make a circular motion. So, from the formula of the centripetal force, we know that the factors affect the magnitude of the centripetal force are the mass, linear speed, and also the radius of the circle path. From this formula, we know that centripetal force is directly proportional to m and v and inversely proportional to r. As the mass increase, the centripetal force increase. As the speed increase, the centripetal force also increase. As the r increase, the centripetal force will be decrease. By using the formula F equals ma and centripetal force, we can derive formula of centripetal acceleration. We have ma equal to m times v squared over r, then we rearrange the formula, and we get a equal to v squared over r. Where a is centripetal acceleration, v is the linear speed, and r is the radius of orbit. A trajectory, or flight path, is the path that an object with mass and motion follows through space as a function of time. Now let's look at this picture carefully. When the linear speed is low, the flying object will return to the Earth. But, when linear speed is high enough, the object will circulate the Earth, but not return to the Earth. By using the Newton's universal law of gravitation and centripetal force, we can derive the mass of Earth formula. Let's the distance traveled by the Moon in one complete circle equals 2 pi r. And the linear speed of the Moon, v equals 2 pi r over t. When Newton's universal law of gravitation equals centripetal force, so we have equation 1 equal equation 2. If we rearrange the formula and substitute the v square with the linear speed of the Moon in the equation, at the end we can get the mass of Earth formula. M equals 4 pi r square times r cube over capital GT square. Now, let's solve the problems involving mass of Earth formula. The diagram shows a satellite at 356,830 kilometers height from the surface of the Earth. Calculate the mass of the Earth if the period of orbiting the Earth is 86,400 seconds. Is given, radius of the Earth equals 6,370 kilometers and g equals 6.67 by 10 to the power of minus 11 net 1 meter square per kilogram square. To get the answer, we need to identify the information using the symbol. T equals 86,400 seconds, small r, is the radius of orbit, equal to radius of Earth plus height of the satellite from the surface, which is 6,370 plus 356,830. And we have the value of 3.63 by 10 to the power of 8 meter, and g is gravitational constant equals 6.67 by 10 to the power of minus 11 Newton meter square per kilogram square. Then, we write down the suitable formula. Substitute numerical values into formula and perform the calculation. Finally, we write down our answer with correct unit. 3.79 by 10 to the power of 27 kg. Example 2. The diagram shows planet Jupiter orbiting the Sun. Radius of the orbit is 77.81 by 10 to the power of 7 km and the period of orbiting is 4,323 days. Calculate the mass of the Sun. Is given. Universal constant, g equals 6.67 by 10 minus 11 Newton meter square per kilogram square. Using the same techniques. Identify the information using the symbol. Then, Write down the suitable formula. Finally, substitute numerical values into formula and perform the calculation. We will get the mass of the Sun is 1.99 by 10 to the power of 30 kg. When you were in Form 3, you knew about the Kepler, was a German astronomic, mathematician and astrologist who modified the heliocentric model according to Kepler's law. Kepler's laws of planetary motion in astronomy and classical physics, laws describing the motions of the planets in the solar system. So, in this section we are going to recap the Kepler's law and the techniques to solve the structure questions. Kepler's 3 laws of planetary motion can be stated as follows. Kepler's Law 1, which is also called as Law of Orbit, it stated that all planets move about the Sun in elliptical orbits, with the Sun at one focus. Kepler's Law 2, which is also called as Law of Area, it stated that a line that connects to the Sun sweeps out equal areas in equal lengths of time. And Kepler's Law 3, which is also called as Law of Period, it stated that the square of the period of any planets is directly proportional to the cube of the radius of its orbits. Now, we will be going to do some revision of these 3 laws, before we try up the problem-solving questions. Let's the journey begin. According to the Kepler's first law, all the planets move in elliptical-shaped orbit with the Sun at one focus. Ellipsis has 2 foci, and Sun is always out of the focus. Major axis is the longer than the minor axis, but usually almost the same for solar system. Radius of orbit is the average value of the distance between planet and Sun. Perihelion point is a place where the planet closet to the Sun, and the aphelion point is a place where the planet furthest to the Sun. Now, let us look at Kepler's second law. According to the Kepler's second law, a line that connects a planet to the Sun sweeps out equal areas in equal times. If you look at the diagram, area of region 1 will be equal to the area of region 2, and the time taken from A to B is equal to the time taken from C to D. Since a B covers more distance compared to CD within the same time span, a B is faster than CD. Kepler's third law stated that the square of the orbital period of any planet is directly proportional to the cube of the radius of its orbit. Here are some remarks. If applied the law to planets and Sun, m is the mass of the Sun. If applied the law to the satellites and the Earth, m is the mass of the Earth. A planet which orbits with a larger radius has a longer orbital period. Planets which are further from the Sun take a longer time to complete one orbit around the Sun. The larger radius, the longer time. Or we say, radius increases with time. The ratio of the square of an object's orbital period, with the cube of the semi-major axis of its orbit, is the same for all objects orbiting the same primary. Then, we have the formula as shown below. This picture shows the time taken by different planets to complete one orbit around the Sun. We can see that a planet which orbits with a larger radius has a longer orbital period. We can derive Kepler's third law by using the Newton's universal law of gravitation and centripetal force. Let's the distance traveled by the planet in one complete circle equals 2 pi r. Then, the linear speed of the planet, v equals 2 pi r over t. The planet orbits the Sun. So, therefore the gravity provides the centripetal force. So, we're gonna set the Newton's universal law of gravitation equals centripetal force. And we have equation 1 equal equation 2. The mass m cancels, as well as an r. Then we have the equation gm over r equal to v square. Substitute the v with the linear speed of the planet. Rearrange the formula to get t square. From Kepler's third law, t squared is directly proportional to r cubed. Hence the value of 4 pi 2 over gm is a constant. The ratio of square of the period of any two planets revolve around the Sun is equal to the ratio of the cubes of their mean distances from the Sun. So, we have the formula, t1 square over t2 square equals r1 cube over r2 cube. Kepler's third law can also be applied to the system of satellites and the Earth, with m referring to the mass of the Earth. As already mentioned before. Now, let's have some practice problems. Figure 1 shows the planets, Earth and Mars, orbiting the Sun. A. The radius of the orbit of planet Mars can be determined by comparing the orbit of Mars with the orbit of the Earth. What information is needed to determine the radius of the orbit of Mars? The answer are 1. Orbit period of the Earth. 2. Orbit period of the Mars. 3. Radius of the orbit of the Earth. Question B. The radius of the orbit of the Earth is 1.50 by 10 to the power of 11 meter. Orbital period of the Earth and Mars is 1.00 year and 1.88 years respectively. Calculate the radius of the orbit of Mars. To solve the questions. Step 1. List the information in symbols. Step 2. Identify and write the formula. Step 3. Substitute numerical values into formula and perform the calculation. We will get the value of radius of Mars orbit is 2.28 by 10 to the power of 11 meter. Example 2. The diagram shows a satellite orbiting the Earth at 230 km height in period 1.53 hours. What is the radius of Moon's orbit, if the period of the Moon orbiting the Earth is 27 days? Given that the radius of the Earth is 6,370 km. Solution. Now, list the given information in symbols. T1 equal to 1.53 hours. R1 equals R plus H, equals 6,370 plus 230, equals 6,600 km. T2 equal to 27 days. We need to change it into hours, so 27 need to times 24 hours, equals 648 hours. ZAR2 is the radius we need to find out. Now, write down the suitable formula. Substitute numerical values into formula and perform the calculation. We will get the value of radius of Moon's orbit is 3.72 by 10 to the power of 5 km. We almost come to the end of this video. Let's move on to the subtopic 3.3. Any object, natural or human-made, that moves around another object which is bigger in size is known as satellite. Do you remember? Gravitational force is needed to give the centripetal force for the satellite to move around the Earth in a fixed orbit. The satellite will move in an orbit at a certain height with a certain linear speed. Centripetal force equation and the Newton's universal gravitational law equation are used to derive and determine the linear speed of a satellite. The following steps can be followed to derive an expression for the orbital velocity of a satellite. As the satellite orbits Earth, the gravity provides the centripetal force. So, we're going to set the Newton's universal law of gravitation equals centripetal force. And we have equation 1 equal equation 2. The mass m cancels, as well as an r. Then we have the equation gm over r equal to v square. To find the v, we square root the gm over r. Where m is the mass of the Earth, g is the gravitational constant, and r is the radius of orbit. We know that the r is the radius of the orbit of the satellite. Hence, r can be written as the radius of the Earth r plus the height of the satellite from the surface of Earth, h. Form the equation. Can you determine what is the factor affecting linear speed of a satellite? Yes. The answer is the radius of the orbit. What is the relationship between linear velocity and radius of orbit? Linear speed is inversely proportional to orbit radius. It means that when the orbit radius increases, the linear speed decreases. What will happen if a satellite at a certain height from the surface of the Earth moves around the Earth with linear speed lower than the minimum value? Explain what will happen to the satellite. The satellite will fall to the lower orbit and continue to orbit near to the Earth because the gravitational force became greater than the centripetal force. When the satellite moves into atmosphere layer, the friction between the and the satellite will produce a lot of heat and will cause the satellite to burn. Now, let's try up this questions and answers. A global positioning system, GPS, satellite at an altitude of 20,200 kilometers from the Earth. What is the linear speed of the satellite? Identify the information using the symbol. Then, determine the radius of the orbit of satellite, r. Write down the suitable formula. Substitute numerical values into formula and perform the calculation. Where g is the universal constant, m is the mass of the Earth, r is the radius of orbit. And we can get that the linear speed of the satellite is 3.87 by 10 cubed meter per second. Satellites come in a variety of shapes and sizes, and perform many different functions, but they all have several things in common. There are two categories of satellite, geostationary and non-geostationary satellites. Both categories of satellites orbit the Earth. The linear speed and the orbital period can be determined by using the common formula as shown in the table below. Now, let's recall the difference of the geostationary satellites and non-geostationary satellites. For geostationary satellites, its position always in a special orbit named the geostationary Earth orbit. It moves around the Earth in the same direction as the direction of the Earth's rotation on its axis. And the orbital period t equals 24 hours, that is the same as the period of rotation of the Earth. However, for non-geostationary satellites, it normally in a lower or higher orbit than the geostationary Earth orbit. The direction of rotation must not be the same as direction of rotation of the Earth, and its orbital period is shorter or longer than 24 hours. Besides, geostationary satellites always seem to be stationary by an observer at the surface of the Earth, it always above Earth equator, and used to communicate throughout the whole world. Example like MESIT. For non-geostationary satellites, it always seemed to be changing position by an observer at the surface of the Earth because it orbit above different geographical locations at different times. And it is used to get the information for weather broadcasting, GPS and imaging the Earth's surface. Example like tying SAT, Razak SAT, Pipit, ISS. Escape velocity, v, is the minimum velocity needed by an object on the surface of the Earth to overcome the gravitational force and escape to outer space. If the distance of an object from the center of the Earth is r, the mass of the object is m, and the mass of the Earth is capital M. Escape velocity is achieved when the minimum kinetic energy of an object is able to overcome its gravitational potential energy. If you look at the formula below, can you tell me, what are the factors affecting the escape velocity of an object from the surface of the Earth? Yes, the answer is the mass of the Earth, m, and the distance of the object form the center of the Earth, r. Question 2. Does the mass of the object affect the escape velocity? The answer is no. As conclusion, the escape velocity, v, of an object depends on the mass of the Earth, m, and the distance, r, of the object from the center of the Earth. Its velocity of release does not depend on the mass of the object, m, released into outer space. The diagram below shows how fast a rocket would have to go to leave every planet. If we look at the calculation below, do you know why the escape velocity from the Earth is very high, which is 11.2 kilometers per second? Yes, it is because the Earth has very large mass. Now, let us recall the benefits and implications of escape velocity. 1. Earth is able to maintain a layer of atmosphere around it. This is because molecules in atmosphere has velocity, which is lower than Earth's escape velocity, so that molecules unable to escape to outer space. 2. Planets and jets won't escape to outer space because both have speeds lower than Earth's escape velocity. 3. Rockets need to be launched into outer space have to use a lot of fuels to produce large thrust to produce high velocity that is larger than Earth's escape velocity. Let's look at the escape velocity of other planet. Escape velocity of Mars is low, therefore, the gases are easier to escape to outer space. This causes the density of the atmosphere on Mars to be low, which is 100 times less dense than Earth's atmosphere. Jupiter, on the other hand, has such a high escape velocity that hot gases on its surface cannot escape into outer space. Knowledge on escape velocity is important to determine how spacecrafts can land and take off safely from a planet. Now, let us try this. The Moon and the Sun are two bodies in the solar system. Table 1 shows the values of the mass and radius of the Moon and the Sun. Compare 1. Gravitational acceleration on the Moon and the Sun. 2. Escape velocity from the Moon and from the Sun based on data provided in Table 1. Using the same techniques, identify the information using the symbol. In this question we can see the symbol M, capital R. For G, you need to know it is the universal constant, which is equals to 6.67 times 10 to the power of negative 11 Newton meter square per kilogram square. Then, write down the suitable formula. Substitute numerical values into formula and perform the calculation. And we can get the gravitational value for the Moon and the Sun. To determine the escape velocity, the following formula is used. Substitute numerical values into formula and perform the calculation. From the answer, we know that the Moon has low gravitational acceleration and escape velocity because the mass of the Moon is smaller than that of the Sun. The Sun is the largest body in the solar system. Gravitational acceleration on the Sun and escape velocity from the Sun have the highest values compared with those of the Moon as well as other planets. Even though There are a lot of formula in this topic. In SPM you may find them in the formula list. The most important thing is, get yourself prepared with the knowledge and understand the important concepts and laws for this topic. Then, you will be able to answer the questions easily. By the end of this section, you may try to check your understanding by answering the following 5 questions in Section A. Scan the QR code below to get the questions and answers. You may try out more questions in Section B and Section C.